This is a stochastic processes, Model 7, Brownian motion and its properties. Lecture 1, Definition and Properties. In the last 6 models, we started with the review of probability as one model. Then the second model, we discussed the definition of stochastic process and its properties. And in the third model, we have discussed the stationary process and its all the properties. Fourth model, we have discussed the discrete time Markov chain. And in the fifth model, we have discussed the continuous time Markov chain. In the sixth model, we have discussed the martingale. And this is the seventh model, that is Brownian motion and its properties. In this lecture, in this model, we are planning to discuss the important stochastic process, that is Brownian motion. And then later we are going to discuss the process derived from the Brownian motion. Then we are going to discuss the stochastic calculus, and followed by that we are going to discuss the stochastic differential equation and Ito integrals, and the application of the Brownian motion, stochastic calculus, that is in the financial mathematics. So we are going to discuss the applications of Brownian motions as in the financial mathematics. So with that, the module 7 will be completed. And this is the lecture 1 of module 7, Brownian motion and its application. In this lecture, we are going to discuss the random walk and the definition of Brownian motion, then how one can derive the Brownian motion using a random walk, and some important properties of Brownian motions also will be discussed. The long-studied model known as a Brownian motion is named after the English botanist Robert Brown. In 1827, Brown described the unusual motion exhibited by a small particle that is totally immersed in a liquid or gas. It is introduced to model the price movements of stocks and commodities. A formal mathematical description of Brownian motion and its properties was first given by the great mathematician Norbert Wiener, beginning in 1980. Therefore, the Brownian motion is also called it as Wiener process. Now we started with the random walk, because using this random walk we are going to derive the Brownian motion. Consider a trial whose outcomes are success with the probability p or failure with the probability 1 minus p. Repeat the trial infinitely many times. That is equivalent of saying tossing a fair coin infinitely many times. The successive outcomes are denoted by the sample W that consists of W1, W2, W3, where each one is the outcome in the nth trial. That means W1 could be head or tail. Similarly, W2 could be head or tail, and so on. For example, we have given HTT or THT and so on. So this collection is this all the possible W's, that is going to be the sample space. Now we are defining the random variable xj. It takes the value 1 if the outcome of the jth trial is head. If the outcome of the jth trial is tail, then the value is defined for xj is minus. So this is a real valued function, and this will be a random variable. Since it takes a value 1 or minus 1, this is a discrete random variable, and one can find what is the probability mass function for the random variable xj. So since the trial whose outcomes are success with the probability p, success is nothing but heading ahead, and the failure is nothing but a trial land up with the tail. Therefore, the probability of xj is equal to 1. That probability is call it the wj is equal to head, that call it as a success. Therefore, this probability is p. And the probability of xj is equal to minus 1, that is 1 minus p. And this you can denote it by q. Therefore, p plus q is equal to 1. You can denote 1 minus p as a q. Hence, p plus q equal to 1. Now we are defining the sequence of other random variables. That is, started with s0 is equal to 0. We are defining sum of first k random variables as a sk, where k is running from 1, 2 and so on. Here xi's are IID random variables, and the sequence of random variables xk, that is a random walk with the s0 is equal to 0, and the sk's are nothing but the first k xi random variables. You can see the sample path of the random walk. Suppose w1 is a tail, therefore it takes a value x1 is minus 1. Again, if suppose w2 is t, then x2 also takes a value minus 1. Suppose x3 is also t, then x3 also takes minus 1. Therefore, sk will be, initially it is 0, then s1 will be x1, that is minus 1. S2 will be x1 plus x2, that is minus 1 plus minus 1, that is minus 2. So S2 is minus 2. S3 will be S2 plus x3, that is again adding minus 1. So S3 will be minus 1. Like that, it can take the different values. So here this is a one sample path with W1 is equal to t, and W2 is equal to t, and W3 is equal to t, and so on, with the probability p is equal to 0.045. This is the probability of success, or probability of getting a head when you toss a coin. So we are going to conclude later, as k tends to infinity, using central limit theorem, one can conclude this will be a Brownian motion. For that, you should understand how the SKs are created, where SKs are the sample path, where SKs are the random walk. Now we are going to see the properties of random walk. If you choose non-negative integers k0, k1 and so on, then if you find the difference, the difference is nothing but a sum of xi's in this range. Since xi's are IID random variables, if you take a non-overlapping intervals or the increments of si's, then that will be mutually independent, because each these increments will be nothing but the sum of a few xi's, and we know that each xi's are mutually independent IID random variables. Therefore, non-overlapping increments will be a mutually independent random variables. Hence, Sn has the property called the independent increment property. The increments are independent. Similarly, for 0 less than or equal to I less than or equal to j, Si minus Sj is identically distributed with Sj plus h minus Si plus h for h belonging to natural numbers. Hence, the stochastic process Sn has a stationary increment property. That means if you find out the n-dimensional random variable and shifted by h, find out the another n-dimensional random variable, if though the joint distributions are same for both the n-dimensional random variable without shifting and with shifting, then that stochastic process is called a stationary. But here the stochastic process is not a stationary, the increments are stationary. That means if you have a increments and you shifted the increment by some interval h, then the distributions are going to be identical. That's what it shows. For 1 less than or equal to I less than j less than or equal to k less than L, the difference, the distributions are going to be same as long as the length is same. So it is the increments are time invariants, not the actual stochastic process. Therefore, this stochastic process has the stationary increment also. So therefore, the random walk has increments are stationary as well as independent. Also, one can find mean and variance of increments. The increments are nothing but the difference of those random variables. And since each random variable or discrete type random variable with the probability mass function that is discussed in the previous slide, so we can find out the mean and variance of those random variables. Therefore, we can find out the mean and variance of increments also. Now we are going to derive the Brownian motion using random walk. Consider a particle performs a random walk such that in a small interval of time of duration delta t, the displacement of the particle to the right or to the left is also a small magnitude delta x. Whenever a particle performs a random walk in a very small interval of time delta t, the displacement of a particle to the right or to the left, that magnitude is delta x. Now we are defining a random variable s of t denotes the total displacement of the particle. In time t, let xj denote the length of the jth step taken by the particle in a small interval of time delta t with the probability mass function. So the probability of xj takes the displacement of the particle to the right side, that is delta x with the probability p, with the left side, that is xj takes a value minus delta x, that is 1 minus p, that is nothing but a q, where p plus q is equal to 1, where p is independent of x as well as time. That is very important. The probability of the displacement to the right or to the left, that probability, whether p or 1 minus p, which is independent of x as well as time. Now the partition of the interval of length t into n equal subintervals of delta x. Then n times delta t becomes t, and the total displacement s t is the sum of n IID random variables xj. The way we partition the interval 0 to t into n equal parts, therefore the s of t, the total displacement, is nothing but the sum of n IID random variables xj's. where n is nothing but n of t, because you are partitioning the interval n, you are partitioning the time interval 0 to t, the length t, into n parts. Therefore, n is nothing but n of function of t. That is nothing but t divided by delta t. So you know the mean and variance. Therefore, you can find out the mean and variance of s of t also, because st is the sum of n IID random variable sales change. Expectation is a linear operator. Therefore, n, since it is IID random variable, n times expectation of any one random variable. Whereas variance, since the random variables are independent, then the variance of s of t is nothing but variance of sum of random variables. So you can take it out and you can do the simplification.